Okay. So we're going to start with almost the last talk. So next up is Francois Charton from Meta AI, who's going to talk about math with transformers.
Yeah, can you hear me? Does it work? Yeah, good. So I'm Francois Charton. Yes, I work in Meta. I'm going to talk about math, but maybe sub-undergraduate math, just to be clear, with transformers. So basically what I'm interested here, I usually summarize it as AI for math. I'm using language models, so transformers mostly, to solve problems of mathematics. And I'm doing this by setting those problems as an instance of a translation task. So basically, I'm saying I want to translate a problem into its solution, like I would translate two languages. So one, mathematical expression into another mathematical sentence. And for this, I'm going to leverage the transformer architecture, and I'm going to train a transformer from generated data sets of problem and solution. So this is a long series of papers. We've been working with several collaborators for more than 3 years now. So I'm going to talk mostly about those 5 papers, and there's 3 more. The first one will be discussed by Amaury just after me. Second one, no. And the last one was discussed by Christine yesterday, Christine Lauter, about cryptography. So a few words about transformer. I'm not going to explain how they work. It's an architecture that was originally intended for translation, for machine translation. And so they translate sentences from natural language. So they represent all their input and output as sequences of tokens, just like sentences as sequences of words. And they learn to transform, or translate, if you prefer, one sequence into another. They're called sequence-to-sequence models, seek-to-seek models. And they started as tools for translation, but over the years, they've become some kind of very generic architecture, and they've become state-of-the-art on a very wide range of problems. So now you get them in translation, obviously, but you also get them in vision, in speech, and sometimes in science too. And the way they work, transformer, they've become very fashionable for a couple of reasons. But the most important one is that so long you're able to translate your problems and solution, or represent your problems and solution as sequences, and so long you have a lot of training examples and some compute, you're okay, you're good to go. Because you don't need to input inductive bias. You don't need to input, problem-specific data, or to do a lot of feature engineering on your data. You just need to have a lot of data fit into sequences, and that's all you need. So this makes them very applicable to a wide range of problems with very little work on the data. So that's nice, at least from a transformer trainer point of view. So the question we asked 3 years ago with Guillaume Lample was, okay, could we use them for math? So there are reasons why it might look, or it could have looked like a good idea at the time. The idea that math is a language is relatively obvious. The fact that problem solving can be understood as translation is maybe less obvious, but it's, when you get used to it, it makes sense. And the large data set requirement is not a requirement in math. I mean, it's not a problem because you can easily generate lots of problems and solutions. So you have the data. Of course, there are reasons to think that this is a bit wonky because neural networks struggle on very, very simple mathematical problems. For instance, integer multiplication with MLP is tough. There are a few papers that can do it in binary numbers or for very small numbers with like 2, 3, 4 digits, but it's tough, and yet it's a very easy operation. The idea also that math could be learned from example only without inductive bias is totally counterintuitive. This is not how we learn math. We can't learn multiplication just by seeing a lot of multiplication. You learn the rules. And the idea that advanced problem could be solved without rules or theory just by looking at examples seems very strange. At least it's not human math or math as we know them. Okay, usually I have here a slide trying to convince people that it's a good idea, but I won't waste this one on you. So the plan is as follows. I want to use transformers in mathematics, and I'm going to do that first by casting my problem as a sequence-to-sequence problem. So I need to represent everything as solutions, problems and solutions as sequences. Then I'm going to generate very large sets of problems and solutions. And finally, I'm going to train my models. So first question, I need to represent mathematical sequences. So this is relatively easy, but it's always good to say a few things about it. So saying that a mathematical expression is a sequence of tokens, a lot of mathematics is already done with tokens. So basically we have symbols, we have variables, a lot of mathematical constructs like vectors or matrices are basically sequences, so all can be made into sequences very easily. There are just two important issues. How do you want to represent numbers? And how do you represent, complex expressions like functions and equations? So for numbers, for integers, we write integers as sequences. This is the magic of positional notation. 1024 is plus 1024. That's base 10. You could have shorter sequence by using larger bases, like plus 1020, 24, etc. So representing an integer as a sequence is the way we write it. Of course, for real number, we have a problem because as a sequence, it might get a bit longish. So practically, we do as computers do. We represent them. There's always a precision question, so we present them as a base 10. I usually use base 10 floating point number. And then I can represent them as three tokens, say a sign, a mantissa, an exponent. Okay? So I can represent, I'm claiming, and then if I wanted complex number, then there would be pairs of real. Yeah?
Why do you need to solve this problem for real numbers? Because on paper, we don't need to solve it. I mean, the fact that you're writing a real number on paper is a bit longish. It's never prevented anyone from doing mathematics on paper.
Which one?
Why don't you just write square root of 5 plus 7?
Well, the problem is that suppose I want to find an approximation to, I have a matrix, and I want to compute the inverse of the matrix. Most of the time, I'm going to have, approximates of things. So I could make fractions of 1,000, of 10,000, that would be the same representation, that would work. But you might want to, to represent them in a more compact value also.
The kind of question you're asked.
Yeah.
I mean, if I want to inverse a matrix, I just have 1 over 2 at a time.
No.
If you have a problem about pi, then you can just write pi and vice versa.
Maybe sometimes the answer is give the answer to 3 decimal places.
I think in many cases, when you want approximate computation or when you want to use that in physics or science, you're going to need real numbers, I think.
You don't have to write your topological spaces to 3 decimal places.
So let's go for expression. So expression is it's a famous way to represent expression. It's been done in formal systems since at least a century. Expression can be represented as trees, and basically you have the operators that are the internal nodes, and the numbers or symbols, the final symbols that will be the leaves of the tree. So at the left you have the basic thing, 2 plus 3 times 5 plus 2, which is represented as a tree. And then if you get a little more creative with the vocabulary you use, you could add variables, so x. You could have new function like cosine, unary or binary functions, and then you could represent a function, or even if you admit that, for instance, an equation you forget the equals 0, or you don't encode the equals 0, you could add Greek letters for functions, more letters, and you could add differentials, etc., and you would end up here with a wave equation or stuff like that. So pretty much, well, any equation can be represented relatively easily as a tree. And the good thing with a tree is that it's very easy to enumerate a tree. There are ways. And we typically use pre-order enumeration, so normal Polish notation. We could do post-order as well. I think it would work just as well. So you start from the roots and you enumerate the parent before the child and the left tree, subtree, before the right subtree. So you see here, start from the root plus, then 2, right subtree, start from the root times 3 plus 5, 2. And I could,
with parentheses for functions, like the cos 2x,
yeah.
also the next line.
Yeah, the parentheses just disappear here because the tree already knows, the child is the whole argument to the function. And if you have a binary function, you would have 2 children, first argument, second argument. So that's the charm of the tree representation. You don't need it. You would need them if you wanted to do infixed representation of your trees, but then it would be complicated because you would need precedence, you would need a lot of weird details, and if you get a lot of operator, precedence becomes something complicated because you have to define it and compare everything. So usually that's pre-order enumeration is a fast way. So trees are practical for making sequences, but there are two more reasons why I use trees, which I think are important. The first one is that, you representing well-formed expression as trees is a famous way. It exists for a long time. I remember there's a book by Haskell Curry that calls those op systems, which are systems where all the well-formed expression are represented as trees. So the idea is that anything that can sort of work in a formal system will be representable in this way. The second important and more important thing is that we're going to generate a lot of random expression. And what's a random expression? How do you generate a random expression is a difficult idea. But if you think of an expression as a tree, then it becomes easy because you can generate a random tree. Lots of algorithms for that. And then you can randomly sample operators for the internal node from a specific vocabulary, which is problem specific. And then sample, the numbers and variables for the leaves, and then you enumerate and you get expressions. Okay, talking of which, we're going, now that we've made everything into sequence, we're going to generate data, and there are basically two classes of data generating techniques. So the basic way, the stupid way, which is the forward method, basically you generate a random problem, you compute a solution, and you have a pair, problem and solution. You rinse, repeat that 10 millions of times, and you have got your training set, and you're good to go. You can train your model. Of course, the problem with this approach is that it assumes that you already know how to solve the problem. So it works for a problem you know how to solve, and it works only to the capacity of the external solver you have. So if your solver works on only some subset of the problem space, the model will only see that subset of examples. Okay? So another way we use many times is the backward method. It turns out that for many mathematical problems, instead of finding the solution to a problem, it's easy to find the problem to a solution. So you generate a random solution.
What does that even mean? You can't generate a random proof and see which theorem.
No. But if you want to, for instance, we're going to see that for integration. If you want to integrate, you could generate a random function and compute the integral. But you could generate a solution and compute the derivative. And you have many examples like that, where you basically will see that when we do symbolic regression, you want to interpolate through a function. Instead of having points and finding a function, it's much better to have a function, find the points, and exchange the two. So this is a very practical method that happens quite a lot. And finally, so that's small presentation of the transformer architecture we're using. The sequence-to-sequence architecture is basically two transformers next to each other. So there's one that takes care of the input and one that takes care of the output. Think of it as translation, translating from French to English. So the French side, the left part, the encoder, looks at the French data, and the right part produces the English data from the previous English data, previous decoded data, and looking up through something called an attention layer, which is the thing you see at the top, at the French example it's currently translating, right? So this is basically the architecture we're using. So that was the preliminary. Let's go now for the real presentation. So I'm going to present several papers. The first one, which is the original one we wrote with Guillaume Lamp in 2019, was called Deep Learning for Symbolic Mathematics. And we were attacking two problems of symbolic mathematics, basically integration and differential equation. So integration, you have a function and you want to find the antiderivative. And differential equation, which is a glorified version of a previous one, you have a relation between a function and its derivative, so ordinary differential equation in one variable, and first order or second order, and you want to find a solution to that. Why choose these problems? Well, there are a couple of reasons. The first one is that they were interesting because they're advanced problems. It's not just arithmetic. They're taught at, say, university level, so, okay, not cutting edge, but difficult. They're non-trivial even for trained mathematician. I mean, I'm not sure anyone can integrate a function just by looking at it, or, we need to compute. There are techniques, but we need to compute. And they're also difficult for machines. Actually, there's an algorithm for integration, which is called the Risch algorithm, exists since the 70s or 60s, I think. But it's very, very difficult to implement. It's never fully implemented, so it has its failure cases. So it's tough for humans, tough for computer algebra. And then there's the small cheat here. It also involves a lot of pattern recognition, which is something we know neural nets are good at. When I say pattern recognition, I say when you see a function and it has trigs, you know that the integrals will probably have trigs most of the time. If you see an arctangent, you have a guess, of seeing a square root or something like that somewhere in the integral. So there's a lot of pattern recognition. There's the way we do that, and we know it's something that computers do well. So yeah, it was a good idea. So then, after having the problem, we think of data generation. So we have here 3 techniques. So the first one, the forward one, I generate a random function, which is my problem, small f, and I compute the integral with an external tool, in that case, SymPy. Okay, the default of that, it's slow, and it's limited to the only function that SymPy can integral. Most of them, but not all of them. Backwards, okay, I generate the solution, I compute the derivative. This is much easier to do. This is much faster, so 2 samples. And then we had a third sample, which is integration by parts, and at this point you must be wondering, why on hell? And the question, okay, so the idea of integration by part, it's a property of derivation of multiplication. It starts like backward. You generate 2 functions, big F, big G, you compute the derivative, and then you look up in the functions you've already computed. And if you can find small f, big G, then you get big F, small g for free. And why? So it seems that it will never happen, but remember, I'm generating millions of cases, so this actually happens. Why am I doing this? Well, here is the kind of data you generate when you follow the forward approach. Here is the kind of data you generate with the backward approach. You see, forward, backward. So in the forward case, what you can see is that you generate relatively, on average, short function with long integrals. In the backward case, you have long functions with short integrals. Both are interesting in their own right, but it means that the way you generate data sends you explore different parts of the problem space. And of course, it's relevant because the data is the only thing my transformer will see. It knows no math. So, and integration by part then becomes relatively logical because it's kind of a middle of the way road. So we actually thought of it later once we noticed the problem with backward. But yeah, so we have 3 data sets. There's also a trick to generate differential equation. It's in the paper. It's a little more complicated. It's a backward method. So we ended up with 5 data sets between 20 and 40 million equations, pairs of problems and solutions every time. So for the forward, backward integration by part, 3 for the integration, and 2 for the ODE. And on this, we train, a regular transformer. We have functions with up to 15 operators, and the functions are, elementary function. That's the elementary function from Liouville integration theory. And yeah, they have 1 variable and all that. So the results. If you train a transformer to do that, so the first line is what I call beam size 1. The transformer outputs 1 solution. With the transformer, I can ask the transformer to provide the 5 or 10 most likely solutions. So that's many guesses. If I have a verifier, which is the case, then I can give my transformer more chance by giving in, more guesses. But the thing is that if you look at beam size 1 and integration, you're already at 90-something%. So pretty much you can integrate almost everything in a test set. The functions I'm testing here have not been seen at training, so they're totally new functions. If you add beam size, of course, you have more guesses, so you have better results. And so we get close to 100% results, even without beam. And no matter how the data is generated, because when you generate the data, there's always that nagging question saying, okay, is it because my transformer is doing well, or is it because the data I generated happened to be the easy cases? I don't see how for integration, but you never know. So in this case, the fact that you get very good results on the 3 data sets, which use different methods for generation, probably rules out the idea that the transformer is exploiting some ridiculous trick inside your generator.
Integration, is it the same test set for the 3 methods, or?
No. They are the test sets. I'll be back on that. The test sets here are generated with the same generator as the training data. So everyone is tested on there, but I'll show what happens when you don't do that in just 2 slides. So that's for the integration. For the EODE, it's a more difficult problem. We all know that. And as such, the results go down, and it's more difficult to get good results for order 2 than order 1, and order 1 is less than integration. Still, it's way over chains, or etc. It's not random guessing, obviously. And this is obviously where the fact that of having many guesses, beam search, shines. Okay, this is predicated on the fact that I can easily verify that the solution is correct. Basically, I put it in the equation and I check. So how good is this? So to do so, we compared with Mathematica. So we compared actually with Mathematica, MATLAB, and Maple, but Mathematica is the best of the 3 on those. And you can see that whereas we're close to 99% beam size 1 on the data set, with our transformer, Mathematica tops at like 84, 85. There was a time limit, a timeout, but if you increase the timeout, you go up to 86 or 87. So
what was the timeout for beam size 1?
Beam size 1, there's no timeout.
So you ran it for longer?
No, Mathematica needs to wait because sometimes it's very long, and sometimes it just stalls for a very long time. So we added timeout to check that, for Mathematica to find a solution.
Is beam size 1 is it always giving an answer before 30 seconds?
Oh yeah, it gives an answer in half a second all the time.
That is nice.
So integration we do better, and if you look at ODE, Mathematica actually does better than us on ODE order 2 with beam size 1, but again, we sort of beat Mathematica on beam size fixed. So I hasten to add that we're on our own turf. Basically, it's our own data set that we built on our data, etc. So, of course, in different experiments, we might do better. But still, the proof is there that at least we're at the level of Mathematica and probably better, which was surprising because no one expected that.
Mathematica is doing rich.
Yeah, it's doing rich with more or less, intelligent things put in, because rich gets very, very complicated as you go, as you want to handle more cases. So I'm back at the question you asked. So one interesting question on integration is generalization issue. So we're working from generated data, and we're testing from the same data set as the one we trained on. But if we were using that in real life, whatever this means, the trained set wouldn't come from the same generator. So how can we test that? So that's a good idea of having several generators. So here you can see my training data is on the line and my test data is on the column. So if I train on forward and test on forward, yeah, that's great. But if I test on backward, I'm down at 11%. So that's very low. And the beam will help me, but just to 17%. So it doesn't work. Interestingly, if you do the opposite, you might notice that the whole thing is not symmetric. So it's not, the loss of quality is different whether you train on backward and forward. So not all training sets are equivalent. We'll see that again several times. So it doesn't work. And so the question is, how damning is it? Is it good or bad? So first, try to understand. You remember, I showed you this slide. You see that's what the machine is seeing when you're training on the forward data sets. And the machine is going to see that 40 million times. Yes, 40 million examples like that. And that's all the machine is going to see at train time. The only thing it will ever learn about integration. So with this, the machine will soon learn the cardinal first law of integration, which is it is an expansion. It takes a small expression and it turns it into a long expression, which has a couple of fine properties, but it's an expansion. And why is the machine so convinced about this? Because it's in that in every single damn case of the training set. So if you come up at test time with this, which are counterexamples to the examples you've seen at train time, yes, the model doesn't work. If you train a machine to recognize dogs on big dogs and then test it on small dogs, it will fail for exactly the same reason. So understanding the problem suggests, a couple of mitigations. And the first thing is that what would happen if we test it on the integration by parts, so that the third column, and you can see that whereas a forward trained model fails totally on the backward test set, on the integration by part test set, which stands in the middle, the performance are pretty good. So the model can generalize out of domain. It's just that it cannot generalize too far away from the training distribution. And this again suggests an idea on how to cure that. it means if you, instead of having one generator, you mix several, then you get an improvement. So suppose you train on backward plus IBP, so that's the third line. So you have. Yeah, you mix the tree. But I wanted here to have the two and test out of distribution. So if you have backward on IBP and test on forward, then you can see that you double, basically. So it's still out of domain and it still doesn't work that well,
So
but you can do that.
You have something that you generate lots of forwards, and then you train an AI to recognize those forwards, and then you train a different AI to train on back.
Yes, all the AIs are different. But in this example, I'm training only one AI on several, and this is the way the thing improves.
Just on two.
Yeah.
Did it occur to you to train on all two?
Oh yeah, you get 99 everywhere.
You do?
Yeah.
Why are you even telling us about that?
Because it's interesting. Because in practice, we've seen that forward and backward, which look like two pretty good IDs, end up with two totally different training sets. And that when whether you train on one or the other makes a whole difference. Now, I come up with a third data set, and you're happy because if I train on the tree, then I'm good on the... But there are other ways to generate which probably are not accounted for. And if I... So the idea is that...
Failed on the fourth way of generating.
Yes, exactly. So
This is your point.
how do you generalize out of distribution? So this will be a theme of this presentation. So I'm pretty much done with this paper. The main takeaways is that transformer can solve symbolic problem. Translation from symbolic representation into another symbolic representation, in this case integration. They can be trained just from examples without any knowledge or specific knowledge of the underlying problem. But out of distribution generalization is tough, and the generator plays a big role, and we want some sort of diversity on the generator, or rather on the generated data. Okay? So I'm going to quickly show a second paper that we did the next year with Amaury Hayat and a couple of biologists, computational biologists around Benedetto Piccoli from Rutgers. And the idea here is to predict the properties of graphs. So in this case, the input will be symbolic, it will be a graph, but the output will be a number or a set of numbers. So I'm having directed graph that represent flows. There could be proteins, there could be chemicals, there could be cars. And so all the edges are, directions of traffic, and they can be weighted to see how wide the road is if I'm talking of cars. And you have two special nodes, the first and the last one, which are the source and the sink, the input and the output. And I'm asking two questions. Given one of those graphs, I'm trying to train my transformer to say first a qualitative question: does the flow get through? So is there a connected path and no place where everything accumulates and nothing works? And two, quantitative: if there is a connected path, what are the flow at steady state? We can show it's unique, but okay, well, at least one solution would be great. So two different models, two questions. So the idea is that last time in the previous paper, we had looked only at symbolic things. Can we do, symbolic to numeric in this case? And so you want to represent graphs. So how do you represent a graph? Basically, a graph is a number of nodes and then a sequence of weighted edges. And a weighted edge, well, basically, it would be the number of the two nodes and then an edge. So basically, I'm representing my graph as a sequence of edges, which are each represented as 3 tokens, plus the number of nodes, because I need to know how many nodes I have total. And the output, well, qualitative, it's a 0 and 1, and binary, it's I just enumerate the values and write them after the other. Okay? So we have data sets. So to create data sets, we generate data sets. So in this case, we generate random Erdős-Renyi graphs. With different size, so we go from small size 8 to 32 nodes to very large ones, 100 to 259, 6 nodes. Everything is predicated there on the length of the sequence. Transformers tend to struggle when the sequence gets long, so we try to avoid that. And we compute the stability result. So the stability result, typically you want to invert a grounded Laplacian. So you compute the Laplacian of the corresponding graph, and it's akin to kind of matrix inversion. So it's a complex operation. It's an operation we know how to solve, but mathematically it's a much more complex operation than just addition, division, or basic arithmetic. And what's interesting, so for the qualitative result, we get almost 100%. And what's interesting is that we get that with extremely small transformer. Transformer is only one layer, so it's not even deep learning, it's shallow learning in that case. 256 dimensions, 32 heads, so those are very small. You couldn't use such a transformer for language, for instance, it's too small. And actually, if you reduce everything, you go to 64 dimensions, 8 heads, this becomes ridiculously small. It still works pretty well. So the thing is that this finding a path on the graph is clearly something very easy for the machine, and you don't need a lot of capacity or a very large transformer to handle it. The quantitative result is more complicated. So every time I have a quantitative prediction, I predict to some tolerance, here 5%. So solution is correct if all the numbers are within 5% of the right values. And you can see that we're within 5% for all size, for small, medium, and large. Typically, there's no need to scale the transformer for a larger problem, which is not what people observe in language, but we observe it here. It's not always the case in math, but it's the case here. And we get, a level of prediction which is fairly high. And the models are still relatively small. They're a bit bigger, but still relatively small by transformer, and they tend to be asymmetric. You need a big transformer to process the graph, the input. But to compute the results, you need just a small one. It's a shallow one, actually. And these asymmetric transformers pop up pretty much every time I try to do math. So the results you get there show that those two problems, which seem, a little more, therefore, for sure, they're not pattern recognition like before. They're mathematical problem, and I'm computing something, so I'm processing some symbolic data and transforming it into something numerical, doing some advanced, slightly advanced mathematics, but things like, computing a Laplacian, inverting it, stuff like that, seem to pose absolutely no problem to my relatively small transformers. Yep.
Just a quick question on that asymmetric stack. Is it that performance degrades if you make the one side larger, or that you support to have a smaller?
So it depends. It's a good question. It depends on the task. On some tasks, if you have two very large transformers, you have sort of too many parameters, and it has difficulty training. Whereas the short transformer, I have case in crypto, for instance, having a very, very shallow decoder is important. You won't retrieve the secret in crypto without a shallow decoder. Sometimes it's just saving on the parameters and showing off that you can use one layer stuff, basically. So I wanted to look at the out of distribution performance. So I don't say here, I'm cherry picking, I'm not saying what doesn't work. What doesn't work is that model trains on one size of graph do not generalize on a different size of graph. And this is a generic properties. We have sort of ways to go around it, but practically...
A big graph can't do a small graph.
Yeah, the funny thing is that a small graph, if you train on, 8 to 32 nodes, and you want to predict graphs with 32 to 64 nodes, it will fail. You'll get 0%. Because basically the transformer has never seen that. So it has no way to imagine because it only was from example. And the funny thing is that, it also works the other way. If from big to small, it doesn't work either. And this is something we see a lot. But you can generalize to different things. So I change the proportion in the example. In training example, I have more or less 3 edges per node. Erdős-Rényi, you decide on the proportion, that's how you generate. And if you have graphs with less edges or more edges, it's fine. There's absolutely no problem learning that, both on a qualitative and a quantitative level. So no problem with the structure of the graph, how dense or not dense it is. Also, I try to use different generators. So take that with a grain of salt, because scale-free graphs on 32 nodes is not quite a serious method, but practically non-Erdős-Rényi graphs with different structures, we generalize with absolutely no problem to them. So the system is relatively resilient. It's not resilient to everything, but there is some kind of robustness. Again, out-of-domain generalization sometimes works.
If the graph is too small, you could just literally extend it by sticking a whole bunch of U-curves.
Yes. Actually, there are ways to trick the machine to learn that. For instance, if you put a lot of small graphs and a few big graphs, usually this will be enough for the machine to learn all the difference. I do that for arithmetic. I do that very often. You train on 5 digits, and then you add a couple of 9, 10 digits, like 1%, 0.5%. And that's enough for the thing to be able to do anything between 5 and 10. So it sort of works. Okay, main takeaways. So not only can you do symbolic to symbolic, but you can also do symbolic to numeric. And you can use small transformer and asymmetric architecture, and you can do more advanced numerical computation, like here, linear algebra and stuff like that. So we saw that multiplication is difficult, but not all mathematical computation operations are difficult. Those can be learned, obviously. And there is some out-of-distribution generalization. So I'm not fast. So this, I'll be very quick on this one. This is the third paper at the beginning of the year. I exchanged the thing. Now I have numerical entries, and I want to find a symbolic output. So basically, we're trying to solve one problem, which is, think IQ test. I have a sequence of integers, and I want to predict the next term. And there are basically two approaches to that. Pure regression, so I just look at the number very hard, and then I use this to predict in time series fashion, if you like. And then a symbolic regression, which is probably what you do in your mind now if you try to solve my problem. You try to find, a function and then use it to compute. And actually, you probably try to find a recurrence instead of a closed form formula, because this is the way we handle everything. So we consider two cases. So we're going to compare the numeric and the symbolic approach. Symbolic seems, it's what we do, but it seems more complicated, because you have a step up before computing the values. So how good is it? And we will consider two cases, integer and real sequences. So we generate the data by, that's typical backward approach. We generate a random function, a random recurrence. We initialize it on a couple of points, generalize, get a sequence. And then in the symbolic case, we train the model on the input point and want to find a function, and we will then evaluate it on how well it computes the next points. And in the numeric case, we just give two sets of points, the first points and the last point, and we see how well it does. And what you can see here, the table is the one important. So I'm comparing for integer and float recurrences, the symbolic case to the numeric case. So in the symbolic case, I'm predicting a function and then use it to compute the next numbers. In the second one, I'm trying to do everything at once. And you can see that the symbolic is beating the numeric all the time. So my functions are recurrences, so I'm in domain all the time. But it's interesting because, again, intuitively, you would think that modeling and then computing is a more difficult problem. But, there might be a reason why we do that.
It's like writing the proof and then the
yes.
proof and then the answer.
Exactly.
Just guessing the answer.
Exactly. So here are a couple of success and failure cases. Left is success, right is failure. You can see that there's no principle to this. Practically, sometimes you succeed on easy case, sometimes you fail on easy case, sometimes you succeed on bad case, on hard case. Sometimes the failure is just 1 or 2 points wrong, and sometimes it's totally wrong everywhere. So we couldn't find a way that the model understands those things, but it's interesting to see the case. We also try to do out-of-domain generalization, so we have a database for that, which is OEIS, the Online Encyclopedia of Integer Sequence. Not all of them are recurrences by large mean. And you can see that when you're out of domain, you suffer a lot. So we go from 90%. Oh yeah. And so we still can predict. With the symbolic, we still can predict 33%. But the numeric model becomes better this time because lots of sequences are actually not recurrences. So I suspect this is the reason. But again, we compare to the two functions in Mathematica that does that, and it works. We do much better than the.
These are mathematical functions.
Yeah, the two functions are the two functions you would use in Mathematica to find a recurrence.
So you asked to find a linear occurrence, a bunch of data for where
Yeah, you have two recurrence and linear recurrence because the linear recurrence works better when the sequence is linear and a lot of sequences are linear. So we give Mathematica a chance. You can see that the linear works better than the generic fine sequence. Okay? And here are examples of the stuff the machine can find. So it's highly non-trivial in my opinion. And we did a few fun things with that.
So can you go back?
Yeah, sorry.
Your machine solved it.
Yeah, those are things that the machine found. And here's the recurrence they predicted. So you can see it's non-trivial. They can do fun stuff. And talking of fun stuff, you could use that to try, when you train a machine with integers, the model only knows integers. It has never seen a float because the float doesn't belong to its vocabulary. So you can try to make it predict a sequence that represents a float. Un equals un plus 1 on 3, or un minus 1 on 3 or something. That's 1/3. And so you could do that. And in that case, the model will try to find an approximation to your float using only integers and expressions. So if you type 0.33333, you get 1/3, which is good. If you type, if you truncate it, it will say, oh, it's a little less, and add you a small exponential to compensate. If you provide pi with enough expression, you get pi because it's in the vocabulary. If you cut it, then it will say, oh, it's 2 times the arctangent of a very large number because, arctangent infinity is pi divided by 2. And so there's a demo. I don't know if it's still run, but there's a demo for that. It's a lot of fun if you want to look. So this is a cute result, but it can do that kind of stuff. Another thing that I really like is that if you take real functions that the model has never seen, so give it an inverse hyperbolic trig. It's not in the data set. The model will find you actually a correct expression for it. It works. But also you can give it a function that the model couldn't model with its vocabulary, like Catalan-Dawson or Bessel functions. And you usually will end up getting a pretty decent asymptotic evaluation. I could even get Stirling formula by looking deep enough inside the beam search. So the model can find approximation to functions. So it's sort of, I would say it sort of learns math.
Are these equal? I think these might be equal.
Oh, the first ones are equal, definitely. Yeah. Yeah. Yeah, this is the formula. It got it. But the last ones are approximations, of course. And sometimes, it finds a recurrence because you ask for it, and sometimes you get a closed formula. So it all depends. Yep.
So do you also find a similar pattern if you, for example, train on really long recurrent sequences?
What do you mean? So we haven't tried very long sequences on this. So practically we're looking for, so I would expect, yes, that if you increase, you would get more sequence. What we couldn't do in this paper was to get better and better approximation, try to feed the result, subtract it and try to predict the residual and all that to get a series expansion and something like that. But that would be something interesting.
I'm asking this because I wanted to understand if the Erdős trainee graphs that you had, there you had like a size constraint.
Yeah.
If that was the issue of the transformer or some inherent issue you have with the graphs.
No, it's here. If you've trained on expression that only have 5 operators, so this is what governs the length, you will never generalize to 10 operators and stuff like that. It's exactly the same problem. It's the length of the sequence. So same, if you have never seen a sequence of 10 numbers as inputs, it won't work. So you need to vary the number of numbers. You still have the same extrapolation problem, but you see that. And last thing, you can look at the way, so the model use integers as representation of exponents of floats or as pure integers. And it knows them as tokens. For them, it's meaningless words. But the model is learning a representation for them, an embedding. So this is a projection of the embedding of a trained model. And you can see that the model, so we project it on the 2 highest dimension, that is Tesny plot. And you can see on the integers, you can see that you have the 0, 1, 2, 3, 4, 5, 10, which is at the bottom. And it sort of follows. And if you look at the top part, the top part, you're going to see the squares. You got 25, 49, 61, 80, 100. And 121. Yeah, I don't know why. And it's impossible to explain why. But the model obviously learned a couple of things about integers. If you look at the exponent on the right, is the exponents of floats. And you can see that the model understood that there's a symmetry. The exponent, when you invert the float, it changed sign. And you get that weird zigzag pattern, which is symmetrical on both sides. I don't understand why. We've tried to think of, what are the highest values. So it seems that sometimes you have the squares or not. But the model is clearly learning some pattern and learning some things about numbers.
Is it open source? We can get embedding function?
What?
Can we get that embedding function with open source?
So we didn't have that. We didn't look at that. I don't know if you could recover it. I suppose so. it would be highly multidimensional. So I don't know if we could, use it.
No, I think he was asking if it was open source.
Yeah, the data is open. All the code is open source. Excuse me. Oh, I'm sorry. So I won't have the time for the physics, but I'll present this one. That's okay. Yeah. So those are two experiments on purely numerical computation, which is linear algebra. So of course I'm shooting a dead animal. Basically, I'm doing something that all the machines can do. But it's interesting to see whether a transformer can do linear algebra, because it's a very common thing, and because we are not in a symbolic realm anymore. It's purely numerical. So what I'm doing is that I look at 9 problems of linear algebra: transposition, addition, dot product, so basic operational matrices, plus eigenvalues and eigenvectors, finding both, and then singular value decomposition, and then matrix inversion. And very quickly, what you see is that everything can be learned by transformer, not very big. So, Well, the thing is that exact integer multiplication is hell. But multiplication plus addition, approximate, because this is, to 3 or 4 decimal precision, works. And this is something that is very puzzling. It seems that exact operations are difficult to do on a transformer, but approximate operations seem to pose no problem. And actually, I could do that for dense matrices between 5 to 30 with almost 100% accuracy. So it always works after some training. Eigenvalues can also be computed with 100% accuracy, and this is more surprising because it's less linear, less expected. And I can do eigenvectors with 97%, matrix inversion with 90%. So it was quite surprising. So I didn't try the determinant, but I should. It's really something that would be interesting to see, but I didn't do it, no. So this is a follow-up paper, and this is what I wanted to present, because at this point we've seen that transformer can do a lot of math. But the question is, do they really learn math? There's a couple of questions you get when you submit those papers and try to get them reviewed. It's, but they don't learn the math, they just parrot. They just copy the statistical inference, or they use some trick that you don't know about linear algebra. I doubt it. But still, they probably use some trick and cheat you, etc., etc. And then people tend to say also, well, when they fail, you never know when they will fail. They fail randomly, and it's unprincipled, and you can predict them, and they hallucinate, because this happens in language. And then they say, okay, you've seen that out of distribution it doesn't work very well. So I want to show on this example then to show how you can use math to actually understand the transformers and understand how they work, how you can use those problems to actually rebuke those three comments. So I'm working on the eigenvectors. And so I'm giving the model a symmetric matrix M. And I'm tasked to find a vector D and a matrix H such that H, M, H transpose is a diagonal with D in the diagonal. Okay, and the model will only learn that from triplets M, D, and H. Okay, so I give it a lot of examples, and it's supposed to predict D and H from M. The model knows only that, but we're educated and we know that from theory that the D will be somewhat unique there, the eigenvalue, so unique up to a permutation. And that H is going to be unitary, actually an orthogonal matrix because it's symmetric, which means that the rows and columns will be 2 by 2 orthogonal and will have unit norms.
None of these things are true.
No?
Are you missing an assumption? I mean, H can just be a diagonal matrix. M and D and H can just all be diagonal matrices.
M and D? Yeah, my matrices are not. No, my matrices are not symmetric. The matrix is dense in this case.
All I'm saying is that
it doesn't.
It doesn't tell us.
Okay, I'm sorry. But you see my point here.
Yeah. I can just multiply if everything is diagonal. You can't.
Yeah, but M is not diagonal in that start. It could be, but it won't be general.
It doesn't tell us.
Yeah, I agree. I agree. Okay, I'll correct it, I promise. I'll never show maths to mathematicians. That's the very last time. Now I talk to physicists only. They're fine. So.
Transpose is H inverse. Fine.
Okay, so let's say, so the thing is that I trained my model to 92% accuracy, which means I got 8% error. And then I'm going to test it on 50,000 matrices that were never seen at training, which means I get 42,000 correct prediction, but 8,000 errors. That's what I'm interested in. I want to look at the errors. And what I noticed is that in 99.9% of the test case, actually all the 50,000 but 6 examples, the eigenvalues are predicted with less than 1% error. So the eigenvalues are right even when the model is wrong. What I noticed is that in almost 99% of the test case, all the rows and columns of H have unit norms. And the model doesn't know that. It learned that from the data. So I'm stating here that this is a good definition of, have you learned some mathematics? In that case, the model learned some kind of invariance from the problem and from the examples that says, okay, in general, even when it fails, you will have those two properties.
So in the training data, the rows and columns of H have unit norms?
Yes, yes, always.
I see.
And the models,
You don't tell it that.
no one knows. Well, we know, but the model doesn't. And so some math have been learned here. And what's interesting is that these results hold even when I don't really train my model hard. I half-train it to 70% accuracy. I still get my eigenvalues right in 99% of test case. And the rows of column have unit norms in, it's 97%, but still pretty good. So, and I tried for a larger problem, so 6x6 matrix, so more coefficient, more difficult. I didn't sweat it a lot, I let the transformer learn for a while, and I ended up with 43%, which is not very satisfactory, but still my eigenvalues are correct, and still the unit norms are correct, which I want to say that the model learns those things, but it also shows that the model doesn't hallucinate absurd error. When the model doesn't know, most of the time it's going to predict solutions that are relevant to the problem, and that have a number of the properties of the desired solution, and some properties that are wrong, the fact actually that the columns are not quite orthogonal. They are almost, but not quite. And what's interesting is that I could very much use that to predict failures. We said failures are in principle, but actually I can predict failures because I know H is not orthogonal. And I can measure that using the condition number of H, which should be 1 if it's orthogonal and larger. And actually I can show that if I look just at the condition number of H, and compare it to 1.03, empirically observed, the model can predict in 99.3% the model outcome. My rule can predict the model outcome. So what I'm saying here is that the failures are very principled. I see the exact same thing for inversion. For inversion, I'm just looking at the condition number of the input, because I know from theory that this is a good predictor of how hard inversion will be, because the matrix is badly conditioned. And the condition number, rule on the condition number can predict 98% of the model outcome. I don't even need to run the model to know the outcome with that. So it's interesting because it shows that the failure not only can be predicted, but they also follow, the rules of some principles of deeper mathematics that we know from theory. So it's interesting because it shows that, something mathematical is being learned. Yeah, you get something wrong. The model will always get you an error, get you an answer, so the answer will be wrong. I would expect that it would be, something, I don't know in which sense it could say close, but something that minimizes something. I haven't tried. I should try that probably. Yeah. So, also on the eigenvalue problem, I want to talk about out-of-domain generalization. Why? Because again, I got a lot of theory I can use, this time the theory of random matrices. So all the matrices I'm generating are Wigner matrices. So I'm generating randomly independent coefficients, either from a Gaussian or a uniform law. So I know from theory that the eigenvalues are distributed according to a semicircle law, asymptotically, and the convergence is relatively fast. And so the eigenvalues will be symmetric around the origin, on average, and they will have, the circle law has pretty much a compact support, so there are bounded values for the eigenvalues. And this is my training set, and this was my test set. So now I'm going to test it on 6 alternative distribution of eigenvalues, which are non-RID matrices with non-RID coefficients. So I had Laplace Gaussian uniform. So you think of a matrix, you take the eigenvalue, replace it by your Laplace distributed Gaussian uniform distributed eigenvalue, recompose it, and there you go, that's your test set. And then I try with positive matrices with, absolute values of semicircle or Laplace distribution. And I also try on Marchenko-Pastur distribution, the eigenvalues of covariance matrices, because they're close to what you could call a real-life matrix. That this is the kind of thing you might encounter, in statistics, for instance. So we test 6 different alternative distribution. And it's as before. So the lines are the training set, and the columns are the test sets. So first line, if you look at the semicircle, so those are my Wigner matrices. And it's as advertised. It works very well on the semicircle, and it fails everywhere else. My model doesn't generalize. It's sort of generalized on uniform Gaussian Laplace, because inside the uniform Gaussian Laplace, there are things that look a lot like Wigner matrices, but that's all you get. And you almost never get, Laplace, Marchenko, and all that. If you train on positive matrices, you will generalize to positive matrices, but not to non-positive matrices. Okay? And this is normal, because you've never seen negative eigenvalues at train time. There's no way you will invent them at test time. But the fun thing are the 2 last rows, because you can see if you train on Gaussian and Laplace, which are non-Wigner matrices, not only can you generalize to Gaussian and Laplace, but also to semicircle, and even to Marchenko-Pastur and the positive distribution, even though there is also almost no positive matrix in the training set. So I'm not only generalizing out of domain, I'm generalizing wildly out of domain to a totally different ensemble. Okay? And so this is interesting. So it shows that if you wisely select your training data, out of domain generalization is possible, at least on this example, I don't know. And the funny thing is that if you use those OOD training distribution, those robust distribution, they are not only better, more robust, but they train better. They train better and faster, even when you test it on Wigner matrices. So if you want to predict Wigner matrices, you're better suited to train your model on Laplace distribution, because you can see here, I use only 36 million examples, this gives you an idea, on 8, 8, and 10, 10 matrices.
What did you train on? You're still training?
So I'm training, you still have the lines, which are the training sets, and the column are the test sets.
You're training on what size matrix?
So you have 8, 8, and then 10, 10 matrices.
You train on 8, 8, and you test on 10.
No, I train and test on the same size. It doesn't generalize to different size. It's always the same. But in this case, the thing is, well, because I only have 30 million examples, and that's not enough for the model to learn for semicircle. But the funny thing is that with the same number of examples, not only the Gaussian and Laplace learn, but they learn 100% on the semicircle test set. So your best deal if you want to predict semicircle is to train on a different distribution in that case. And for the 10-10 matrices, then it's the same. And at that point, what's interesting is that you get the Laplace, generalizing to matrices with positive eigenvalues on 10-10 matrices, and the probability of 10 eigenvalues to be all positive for Laplace distribution is almost 0. So you're really out of domain, but it still works. So what you see here is that out of distribution, it's not really a curse. It's a problem that we have. But it's something that can be solved, and probably the direction you want to have is to have different, there are more robust distribution. My personal hunch is that it's because, Laplace distribution have more large values, so there are more extreme cases. And the idea is that, like when we learn more from edge cases than from averages. So probably training on a larger distribution sort of helps. There might be other, theoretical reasons. But it shows that you can actually show a couple of things on how a transformer learns mathematics. I just have a couple of minutes, so it generalized to other problems. So what I'm saying here is far out domain generalization is possible. Robust generation training set also learn better. And it seems relatively independent of the test problem. I haven't shown that, but I could achieve the same result with the inversion and the eigenvalue vector problem. So it seems that the Laplace is good for a set of problems, not just one problem, which would be the eigenvalues. I'm going to talk about the problem of physics extremely fast. The next idea is to see, okay, can we use that for science, and notably for theoretical physics? So this problem is particle physics, it's the free gluon form factor. So basically, it's trying to predict the outcome of the interaction between free gluons. The gluon is the photon and the strong interaction, the particle that mediates the strong interaction. And you can represent the scattering amplitude, so the amplitude of the different states of this, as a polynomial, as a homogeneous polynomial in 6 variables, 6 non-commutative variables. And the degree of the polynomial depends on the number of virtual gluons that are created during the interaction. It's called a loop. So the way it is done now, so you have key value pairs. So basically, you can represent the problem as a sequence of letters between A and F, and a number, an integer. Most of the integers are 0, and sometimes they're different values. And right now, the non-zero coefficients are computed by hand using symmetries and using PhD candidates, lots of them, because it's really big number computation and stuff like that. And so the idea, we know that there are regularities, and we guess that there might be some regularities that physicists don't know. So could a transformer spot them, using what we've done with the integer series and all that? And so the idea, we have 3 questions. Can we predict zero coefficient? Can we predict a non-zero coefficient from the key? Or could we design some kind of a recurrence that goes from one level to the next? Just to give you an idea, here you have the number of non-zero terms. The best they've done is loop 8, which is 1.6 billion non-zero coefficients. So those are pretty big polynomials. So the idea is very easy. You take the data you have, you select part of the data as your test set that won't be seen at training. You train on the rest and see if you can predict the test set from the training data. Okay? And what you see is that if you try to predict for loop 5, loop 6, you try to predict whether the term is 0 or non-zero, a transformer makes it all the time. It's 99.7, 100% of the time. So predicting a 0 is a no-brainer for a machine. I don't know how it does it, but it does it. Samely, when you try to predict non-zero coefficient, you got those learning curves. And this is fun because you seldom see curves with those 2 humps. So the curve learns very quickly to 50%, and then it saturates, and then it learns again to 100%. But in the end, you learn everything. And the fun thing is that when you predict an integer, you predict an absolute value and a sign. And it turns out that the absolute value is very easy to predict, but the sign is hell. So I went back to the physicist and said, why? And they say, oh, well, we've been working a lot on the sign, and we never manage it. And the guy is very, very strong. So I think, they know the sign is a big problem. And the model does that. You can see it here. So you get some kind of, so the hope here is to, provide enough ideas to try to get, new intuitions on this. And I just wanted to say, predicting the next loop works too. So at this point, this is only, a first experiment in physics, and this is only a proof of concept. There's nothing to be done with it. Well, actually, no. We asked for a grant and got $6 million grant from the Department of Energy. So now we have postdocs to work on it, maybe to compute loop 9. No, seriously, I mean, we could. The transformer says that regularities do exist, and now the question is, how can we find them? So maybe with some variation on, symbolic regression or something like that. How do you recover them? So opening the transformer is probably not the new idea. So we're starting new work on that. So I'm done. I'm sorry I was a bit longish. So main conclusion is that you can learn math with deep language models. It's not really a problem, just from examples. I think it's a new field of research. It's interesting for mathematics because the hope is that now we're solving easy problems, but we know that we can generalize. And if we could generalize, we could try to attack hard problems by training on easy problems and try to generalize to hard. And maybe this works, and that would be fun. And it's interesting for science. If you want to do science end by end, you need to do math. There are math everywhere in science. And I've showed with the matrices that you could do explainability with that. So, yeah. So that's all I had to say. Then Amaury will talk about the more serious problems we have. Thank you very much.